Okay, welcome back. So in this video, we're going to do a couple problems from measure theory. So we're given a measure space such that the measure of the entire space is equal to 1. And we want to do two things. So we want to show that if R and S are positive extended real numbers, that whenever R is less than S, this inequality right here holds. And then we want to figure out under what conditions does this inequality basically become an equality for a function f. So let's start with the first inequality that we're trying to prove here. So this is not actually true in a general measure space. And you can maybe come up with some examples. It's not super hard to find examples of where this fails. For example, in a measure space where the measure of the entire space is equal to infinity. But anyway, so the way that we're going to prove this is using Holder's inequality. And so as a quick reminder of what that says, so if you have two measurable functions f and g, the one norm of fg is bounded above by the p norm of f times the q norm of g. And this is true for any conjugate exponents p and q. So real numbers, both of them greater than or equal to 1, and such that 1 over p plus 1 over q is equal to 1. So this is Holder's inequality. So how are we going to use this for what we're trying to prove? Well, we just have to be slightly clever. So we're basically trying to show that this expression here, so this is the R norm of f, and we're trying to show that this is less than or equal to the S norm of f, which looks like this. But if we raise both sides to the r power and get rid of this exponent, basically we're trying to show that this is true. Okay, so this is where we can use Holder's inequality, because we notice that because r is less than or equal to s, s over r is greater than or equal to 1. And so that means that we can use s over r as one of our conjugate exponents. So what we'll basically do is, again, we're going to use Holder's inequality, and one of our functions is going to be absolute f to the r. So we're thinking of that as kind of like our f. And then our other function is just going to be 1. So basically g is equal to 1. And for our exponents p and q, we're going to have p be equal to s over r, and then we're going to have q be equal to the Holder conjugate of s over r. And it doesn't really matter what that is, but you can verify if you want that it's equal to this. So this is the Holder conjugate of s over r. And this is what we're going to use. So now what Holder's inequality basically tells us is that the integral of absolute f to the r times 1, technically d mu, that this is less than or equal to, so we're going to have the s over r norm of this function. So that is going to be, so we're going to have absolute f to the r, and then we're raising this to the s over r power. So that's going to be absolute f to the s power, d mu. And then we're going to raise this to the power of r over s. And then technically we need to multiply. So we're going to have the norm of, the q norm of the function 1. So technically that looks like this. But the measure of the entire space is equal to x, or is equal to 1 rather. And so this integral in here is just equal to 1. And so this entire thing is just equal to 1. So now we've proven that basically this inequality is true. And if we just go back slightly, so this is the inequality that we were trying to show. And that actually completes the first part of the problem. So it's slightly confusing, but it's really just a clever application of basically Holder's inequality. Great, so now we go back to the second part of the problem, which was under what conditions is it true? So just for a general function f, that the R norm of f is equal to the S norm of f. And again, these are just extended real numbers, and S is bigger than R. And to solve this, we want to recall basically the second part of Holder's inequality. And what that says is, so normally Holder's inequality is an inequality between these two things. So there's a less than or equal to here. But this becomes an equals if and only if there are constants alpha and beta such that almost everywhere this is true. And alpha and beta have to not be both equal to 0. So again, this is just the second part of Holder's inequality. It's pretty fundamental. And so if we apply that to what we just did, right? So remember that we used Holder's inequality, and one of our functions was absolute f to the r, and the other function was g of x is equal to 1. And we got an inequality. And so what this tells us is that inequality becomes an equality exactly when, for some alpha and beta, this is true, basically. And this is what it looks like because, again, g of x is equal to 1. So there's just a 1 here. So basically this tells us that almost everywhere, the value of absolute f of x is beta over alpha to the r, and in particular, it's just a constant. Sorry, that should actually be 1 over r. So this is basically the solution. So if you're on a measure space with measure equal to 1, the only way that for distinct values of r and s this can happen is if f is in absolute value a constant function almost everywhere. And that's it. Back with more videos soon.